Okay, so this video will discuss how we interpret the meaning of the orbital or the wave function. Remember, those two things are the same, or psi, of an electron. And the person who actually came up with a way to interpret the wave function was Max Born, and he said that the square of the wave function specifically corresponds to the likelihood or the probability of finding the electron at a specific value of xyz, or more commonly r theta phi, which is the spherical polar coordinate that people use for representing the atom, because the atom is a spherical object. Okay, and there are three ways to show how this probability can be represented in plots or in graphs. The first one is something we refer to as the linear probability function. This is for calculating the value of psi squared at a specific or a given value of r. So the plot would be looking something like this, where your y-axis would be value of psi squared at a specific value of r, theta, and phi, and the x-axis is just r, or something like a 1s orbital. So the psi squared is actually proportional to 1 over r. As a result, you get a plot that looks like this, where the value of psi squared approaches infinity as r approaches 0. And remember that that's where the nucleus is, right, when r is equal to 0. So this would be the plot for a 1s orbital. Now, you can do this for other orbitals as well. You can do this for the 1s, and here I'm showing you all the other ones. So here's a 2s orbital, a plot for a 2s, a plot for a 2p right here, a plot for a 3s, 3p, and 3d. One thing you want to pay attention to as you go to higher level orbitals, you see that you start to get nodes. Okay, now remember what nodes are. Nodes are the part of the wave where the amplitude is 0. So in this case, the value of psi squared is equal to 0. What does that mean? If psi squared represents the probability of finding the electron at a specific value of r, then psi squared equals 0 means that you cannot find the electron at that space. Okay, so that's really important to understand the meaning of a node. The second way is representing it as something called the radial probability function, which is usually represented as r, as a function of r. So now, what is the difference between the linear probability function, the one we just talked about, and this current new function, the radial probability function? The linear probability function is basically asking the question, if my nucleus is in the middle, as shown by this drawing right here, what is the value of psi squared at this position right here? Now, you remember that the atom is a spherical object, so it makes more sense if I were to ask, what is the probability of the entire spherical slice, okay, this entire space right here? In other words, I just take a sphere that is distance r away, and then add all the linear probability, and what I get is basically the radial probability. It's the product, okay, so you multiply the psi squared at a specific r times the volume slice, okay? You think about this, this is very similar, the atom, to an onion. The nucleus is in the center, and then you have these volume slices that are represented by these purple drawings right here, okay? Now, the volume slices get bigger and bigger as you go further and further away from the nucleus. But to get the probability, the total probability in a specific volume slice, for example, what you're going to do is calculate the linear probability at a specific point, and then just add all of those in the volume slice. So again, the radial probability is just the product of the linear probability times the volume slice. Okay? In terms of an equation, what you get is this is radial probability. Linear probability is just given as psi squared. And volume slice, if you think about it, the volume, this is a spherical thin slice. So in other words, the volume will be surface area times thickness. Surface area of a sphere is given as 4 pi r squared. And then the thickness is given as dr. Now, if you think about these two quantities, the psi square we already talked about earlier is proportional to 1 over r. So as a result, it's going to approach infinity when r approaches 0. That's what we saw earlier with the original plot. However, the second component now is the volume slice component. And as you can see, when r approaches 0, this whole thing also is going to approach to 0. Now, because the volume slice has a component of r squared in it, it's going to approach 0 faster than psi squared approaches infinity. So as a result, When we plot the value of r, the radial probability function for the 1s orbital, what we get is the following shape, which is that as you approach the nucleus, in other words, as r approaches 0, the value of the radial probability function also approaches 0. And this is for the 1s orbital. This is important because what this curve is saying is basically there's a certain distance away from the nucleus where you can have a maximum probability of finding the electron. This is the distance where you're most likely to find the electron, right at this distance right here. And if we do the calculation, what we find is that that distance corresponds to 0.529 angstroms. Exactly the same distance that Bohr calculated to be the distance to his first orbit. This is important because the Bohr model predicts accurately the behavior of electron in a one-electron system like the hydrogen atom. The fact that you get exactly the same number means that the quantum mechanical model is actually valid and you have reasonable physical interpretation that you can get out of the model. So here I'm showing you the two probability functions, the linear as shown on the left column and the radial probability function as shown on the right column. And remember that the only difference is that for the right column you're basically multiplying each function on the left by the volume slice. And as you can see, as a result, we don't see negative amplitude anymore, but what we see is just all positive amplitude. Okay, for the 2s and then 3s, 3p, 3d, all of these are bigger values of n. What you see is that you also have nodes, right? For example, the 2s has a node right at this location. The 3s has two nodes right at this location and this location right here. The 3p has a node at here and also has a node right at the origin, at the nucleus. Okay, so you notice that here, this is the distance where I'm most likely to find my 1s electron, my electron in the 1s orbital. Now, when you shift to the 2s orbital, then the maximum distance goes there. Although, very importantly, there's a little bit of probability of finding the electron also close to the nucleus. The 2p, on the other hand, is just here, right? This is the distance for the 2p, and so on. So what I want you to get out of this lecture is the ability to look at these curves, specifically the radial probability curves, and understanding what these curves are telling you. Okay, so the last way to represent the probability function of psi square is to use something called the boundary surface or the electron density map. This is really the most common representation you will see in textbooks, and what this is basically you're drawing a three-dimensional shape that represents the psi square for a specific orbital. So remember, psi is a mathematical function. And remember, there's a relationship between algebra and geometry. In other words, if you can write an equation, you can also draw that equation. So what this is just a geometrical representation of psi square. What you're going to put in that shape is you're going to put a bunch of dots. The dot density, how many dots you have, would represent the value of psi square in that particular space. The more dots you have, the higher the probability of finding electron in that space. In theory, even at very large value of r, the psi square value is actually not zero. So in other words, you have some very, very tiny probability of finding the electron at very large value of r. But for practical reasons, you can't draw a shape if there's no limit to the drawing. So you have to somehow make a cut and say that we're going to draw it only up to this distance. And that distance is what we refer to as the boundary surface for the electron density map. And this surface, whatever inside the surface, then would cover 90% of the total probability for finding the electron for that particular orbital. So let's look at a drawing of an orbital that represents the 1s orbital. So here, the black dot in the middle is the nucleus, and then all the yellow dots basically represents the probability values for electrons within that space. And as you can see with this drawing, there's a lot more yellow dots near the nucleus than there is as you go further away from the nucleus. This purple surface, which is called the boundary surface, and within the surface, everything, if you were to add all of these things together, they would add up to 90% of the total probability of finding the electron. Okay, but as you can see, for a 1s orbital, you have more dots near the nucleus, which means there are higher probability of finding the electron near the nucleus than as you go further away from the nucleus. Here's a drawing of various orbital shapes and orientations, and you just remember what you want to do is relate these drawings to the radial probability function that we discussed earlier, okay? Which are these things right here. So you want to think about what is each of those drawings that we see for the electron density map and how they represent these probability functions. So remember what I said earlier, that if you're 1s, you don't have a node, but if you have 2s, then you have one node in the radial probability function. If you remember, the drawing was this. You have this and then you have this, right? That's for a 2s. And as you can see, there's one node right here. That node is shown in this drawing also. And then when you have 3s, you have two nodes. You have something like this, and so you have one node here and one node here, and that's also represented by this drawing right here. For a 2p orbital, it looks different. A 2p has a node right at the center, right at the nucleus, okay? And remember, for a 2p, you have three different orientations for a 2p because of the L quantum number is equal to 1, so m sub L could be -1, a +1, or 0. This is what our px, pz, py orbital are. And this is for the d orbitals, where you have 5 different orientations and they all have their own names. And then of course you have f orbitals where there's 7 different orientations. So what I want you to take away from here is just, for shapes, you want to remember the shapes of the s orbitals and the p orbitals. The d orbitals you don't need to remember. You just need to know that there are 5 d orbitals and there are 7 f orbitals. But those are things that you need to keep in mind. But aside from that, you just need to understand how to interpret the meaning of these radial probability functions as well as the electron density map.